Okay, so what if we want to go the other way? We've had some examples where we've parameterized some equations. What if we want to go the other way? So what if they give us an equation that's already parameterized, like x of t is t squared plus 1, y of t equals 2 plus t. They want us to eliminate the parameter because this is actually kind of tricky to graph, right? I mean, the way that we'd have to graph this is make a table and say, okay, if t equals -3, if t equals -2, and so forth. And then we could plot those different xy coordinates. But what if we just wanted to do it in one step, eliminate the parameter, and just write it as a Cartesian equation or a rectangular equation? There are two ways they could say that. Okay, so let's say we have x of t equals t squared plus 1, and y of t equals 2 plus t. Okay, it looks like the easy, here's a strategy. Here we just have a regular t, right? We could solve for that t. We could say t equals y minus 2. And we could plug that then into this first equation. So we could say x equals y minus 2 squared plus 1. Ta-da, the t is gone. It's not any harder than that. Okay, you look at your two equations and you say, okay, which one looks easier to solve for t? Or we'll do different examples. This is if it's a polynomial. Okay, which one looks easier to solve for t? This one. So solve for t and then plug it into the other equation. Okay, and we could multiply this out. Y squared minus 4y plus 4 plus 1. So we could say, x equals y squared minus 4y plus 5. So this we can look at and say, that's going to be a parabola that's opening to the right. Right? We could think about last semester, and it's going to look like this. Okay, and if we parameterized to have our direction, it would turn out to be going in this direction, which is not obvious. I mean, we can't see that from our new equation, but from our parameterized equation, we could say, okay, well, if t equals -3, and have different t values and see as t gets bigger, what happens to our x and y points. Okay, they're going to go along this curve. Okay. All right, let's do a different kind of equation. What if we have an exponential equation that is parameterized? Eliminate the parameter. You have x of t equals e to the negative t, and y of t equals 3 e to the t. And this is just if t is greater than 0. Okay. So again, we could make a table and plot these points, or let's try to write this as just as a Cartesian equation. Well, let's see. I could write this as x equals 1 over e to the t, right, using properties of exponents. So that means I could say, well, e to the t equals 1 over x. And that's helpful because now I could plug that in for e to the t right here. I could get y equals 3 times 1 over x, or y equals 3 over x. Yeah. So here we could see what those graphs would look like. So here's x of t equals e to the negative t, y of t equals 3 e to the t. And that's if t is greater than 0, it's going to look like this. As we plug in different values of t, it's going to move along the curve like this. Okay. Here's what the equation of our Cartesian equation looks like, our graph. Y equals 3 over x looks like this. Okay, so it's actually bigger. This is kind of a restricted domain because they told us t was just greater than 0. Okay, this is what the graph of our Cartesian equation would look like. All right, so what about if we have a logarithmic equation? X of t equals square root of t plus 2, and y of t equals log of t. Which of these looks easier to solve for t? I mean, to be honest, neither one looks super easy, but this one looks easier. We could say, okay, x equals square root of t plus 2. So then I could subtract t. I could say x minus 2 equals square root of t, and I could square both sides. And I get x minus 2 squared equals t. And now I can just plug that into this equation, and I can say y equals log of x minus 2 squared. Ta-da! So just again, you're looking for which equation does it look like I could solve for t in, and then I'm going to plug it into the other. So we solved for t here, and then plugged it in for t in the second equation. All right, here's the last kind of, this is a little bit trickier, and you do have some homework problems where you have to do something like this or understand this relationship. Eliminate the parameter from the given pair of trig equations where t goes from 0 to 2 pi, and sketch the graph. So if I just was going to ask you to sketch this graph, do you have any guesses? Maybe think about it for just 1 minute. All right, we'll see at the end if you're right. How can we do this? So we have x of t equals 4 cosine of t, and y of t equals 3 sine of t. It's going to be easy for me to solve for t in either of these equations. Not really. I'm going to get some inverse trig functions that are going to be a pain. So here's what I'm going to do. Okay, this is the key, and this is like the one trick you have to know. Okay, and all the other equations you're really just kind of solving for t, or like e to the t like we did. Here's the trick. We're going to use the fact that cosine squared of t plus sine squared of t equals 1. Okay, so I'm going to solve for instead of solving for t, I'm going to solve for cosine of t. I'm going to say, well, cosine of t equals x over 4, and sine of t equals y over 3. Right? I just solved each of these equations for cosine and sine. Oh, and now I'm going to use this equation. Well, cosine squared is this. So I'm going to say x over 4 squared plus y over 3 squared equals 1. And hopefully this looks familiar, right? This is, down to a staple here. This is a ellipse, right? Does that look familiar from last semester? It's an ellipse centered at the origin with the major axis along the x direction, 2 units in the x direction, or well, no, this is because this is squared. So it's 4 units in the x direction and 3 units in the y direction, since this is, the whole thing is squared here, right? So if we're going to graph this, here we are. It's this ellipse. Okay, it's 4 units in the x direction, 3 units in the y direction. And we're going this direction, which we could figure out from the original parameterization, right? If t is 0, cosine is 1, and sine is 0. So here we are at t equals 0. And then as t goes, if t is pi halves, well, then at pi halves, cosine is 0, and sine is 1. So here we are. And then back to pi, where cosine is 1, or negative 1, and sine is 0. And then pi halves, and then 2 pi. So we're moving around the ellipse in this direction. That's kind of cool, right? Okay, I think that's the end. So those are the strategies that you can use to eliminate the parameter. Okay, to go from a parameterized equations to a Cartesian equation. Either solve for t or solve for an expression in containing t, like e to the t, or use this Pythagorean identity if you have sines and cosines.